One of the most useful applications of linear approximations is to do with solving equations. So let's say I've got some complicated function f of x, and I can take a picture, I can look at its graph, and it has some point where it equals 0. So I would really love to know what the solution to this equation is. And we're just going to denote this as x equals r. That's the solution to the equation. Now, if the function is complicated, I may not be able to do algebra stuff to find that solution, to find the exact value. So I'm going to have to come up with an approximation to x equals r, and I'm going to do this using linear approximations. So I'm going to assume that the function is differentiable near x equals r, everywhere nearby. And then I'm going to take an initial value. Now, rule of thumb is that the initial value should be kind of close to your solution. Now, I understand that you may not know where the solution is, so you try to get something close, but don't lose sleep over this. It will turn out that the method we use is pretty good, almost regardless of what guess you pick. So you pick some initial value, x1, and then you build a linear approximation centered at x1. So for example, if I were to take this point right here as x1, and I were to draw a tangent line, it would do something like this. Then I'm going to solve the equation of this tangent line equal to 0. And this is going to give me something that I'm going to call x2. So in terms of my picture, x2 will be right there. Now my function, let's say it extends down here somewhere, and I go from there. If I were to then take my equation, so let's say I form my tangent line, I'll have y minus f of x1 equals f prime of x1 times x minus x1. And I would love, I should rewrite it in this way. Let's say that L of x is f of x1 plus f prime of x1. And this, I want this to be 0, and I want to solve for the x here. So if I were to reorganize everything, I would get that x minus x1 would be negative f of x1 divided by f prime of x1. And then if I were to move the x1 over, I would end up with this. x1 minus all of this. Okay, so that's what the solution would be. And then I would call this x2. So why would I want to do that? Okay, now I would build another linear approximation to the function centered at x2. So there's my x2 in the picture. If I go down to here and I build a linear approximation, shoom, it kind of does that. Now here's the key idea. Where it crosses the axis is my next guess, x3. And if I were to then repeat the process, solve for that x3, and then draw a linear approximation, I would find that the more often I do this, the closer and closer the roots of the linear approximation get to the actual solution of my problem. So I will form a new linear approximation, and I'll say its L of x is f of x2 plus f prime of x2, x minus x2. I would solve L of x equals 0 for x. So I would take this equation and solve it, And I would get, once again, x is x2 minus f of x2 over f prime of x2. And then I would call this x3. And then I would just repeat the process. And I would end up with what's called an iterative formula or process, recursive. I shouldn't say recursive, I'll say iterative. And I would find that I would end up with something that looks like this. And what this does is it gives updated approximations to the solution of f of x equals 0. So that root that I started with, that I'm trying to find, I can approximate the value of x equals r using this method. So I pick a starting guess, I form a linear approximation, I see where the approximation crosses the x-axis, and then I use that point as a new starting value, a new center, and then I repeat. Build an approximation, see where the new one crosses the axis, take that value as an approximation and go from there. This is called Newton's method. It's kind of like a heat-seeking missile for solving equations. This is a numerical method to approximate solutions to f of x equals 0. When it works, it's an absolutely amazing method. It will seek the answer to the problem very rapidly. So you may not need very many of these iterations to come up with the solution. If you've got a calculator or some sort of online program like Desmos, most, if not all of these things are programmed using Newton's method to solve equations. And this is kind of the final piece of the puzzle here. We've learned a lot about functions, and now this concept of linear approximations lets us solve equations that we can't solve by hand, and all it requires is just some basic differentiation. So as an example here, I want to say the following. Let's use Newton's method to approximate the value of square root of 5. Now, Newton's method can only work if we write this as some sort of equation. Square root of 5 is a solution to the equation x squared minus 5 equals 0. There's another solution, right? There are two solutions to this equation, but certainly this root 5 is a solution to this version of the equation. So we are going to take this thing, f of x, to be f of x. And certainly this function is differentiable and the derivative is 2x. Now, just to try to tie in some more concepts with what we've done earlier in the semester, I have this function and I know what it looks like. It's a parabola. It crosses at -5 and it kind of does this, right? So I know that this answer right here is root 5, and I know that this answer here is negative root 5. Now, if I were to focus my attention here, since the function goes from negative to positive, and since f is continuous, the intermediate value theorem guarantees there must be a solution to this f of x equals 0. It starts negative, ends positive, somewhere it's got to cross the axis because the function's continuous. You can also use Rolle's theorem to prove that there's exactly one solution here. Now, remember, you've got to stay on the positive side of the x-axis here. And I'm just vaguely drawing some open interval there. But you can prove that there is exactly one solution. And so today's stuff is just the final piece of this story. Before these two theorems, the intermediate value theorem and Rolle's theorem, they're just called existence theorems. They tell you that there has to be an answer, but it doesn't tell you how to find it. Well, now Newton's method tells you how to find it. So we use Newton's method to actually approximate the value of this solution. It's the final piece of the story. In some way, it's very satisfying because it puts it all together. So Newton's method says this, right? It's based on linear approximations, and it essentially boils down to a formula. It's just you solving the equation of a linear approximation equal to 0. Now we know that f of xn, our original function, will be xn squared minus 5. We know that f prime of xn will be 2 times xn. So if I sub all of these things into my expression, I'll get xn subtract xn squared minus 5 divided by 2xn. If I were to put all of this over a common denominator, I would get 2xn squared subtract xn squared plus 5, all of it over 2xn. And at the end of the day, this will give me xn squared plus 5 over 2xn. So it's just a little bit more convenient to work with. You don't really need to do this if you don't want to, but it's just a way to simplify it. So now what we have to do is we have to iterate. And what does iterate mean? It means that you have to start with a value as an initial guess and then go ahead and calculate the resulting, they're called iterates or updated values. Now, you have to choose an x1. It should be near the root. Now, you have to be careful here. When you take an example like this and you use Newton's method, there are a couple of things that could go wrong. Number one, you can't be too far from your root. And too far is vague. So this is the root that we want. Now, I would love to pick my x1 somewhere here because it's kind of close. But don't be too far. If you pick your x1 over here, that means you might converge to the wrong solution. You might converge to this root. And that's no good. You don't want to go there. So Newton's method is a root-seeking method. It just sniffs it out and it finds it. But you have to point it in the right direction and you have to get it close. So if you get too far away, you might actually find another answer. Remember that the business I did with intermediate value and Rolle's theorem there just guaranteed that when I was on the positive side of the axis, I will come up with a single solution. But if I go to the negative side of the axis, I'm going to get another solution. Don't use a point where f prime of x equals 0. So sometimes you can see what's going to happen. If I were to pick this is my starting point, f prime equals 0, Newton's method can't figure out what to do. This tangent line doesn't cross the x-axis. And that means the method can't iterate. right? If you draw this tangent line here, there are no solutions. It doesn't know where to go. It can't seek out the root because it will never cross the x-axis. So if you can avoid it, don't start at a point where you have a horizontal tangent line. You might say, well, what if I'm doing that in the middle of my calculation? Yeah, well, this is one of the downsides of Newton's method. It might crap out somewhere in the middle. So there's not much you can do about that. But for the most part, for functions that we deal with, that isn't really an issue. So how do I pick my root? All right, I should pick something that's close by. I know that I'm working with x squared as my function. I'm going to choose x1 equal to 2. And the reason I'm doing that is because 2 squared is equal to 4, and that's kind of close to square root 5. So now I'm set. I am going to use this, I'll call it iteration formula, and I'm going to use the starting guess of x equals 2. And then I'm going to put all of it into my expression and calculate iterates. How you do that is up to you. You can use a calculator, you can use a software program, whatever you'd like. But it's just a matter of doing some calculations. So that means if I were to pick x1 equals 2, x2 would be 2 squared. It would be the following. Let me even write it more generally. x1 squared plus 5 over 2 times x1. So that would be 2 squared plus 5 over 2 times 2. So that would give me 9 over 4. And 9 over 4 is about 2.25. So now I update. x3 would be x2 squared plus 5 over 2 times x2. So I would take my calculator and plug this in and go from there. Now, at some point, you're not going to be expected to do this with decimals or with fractions, so you're probably just going to end up doing things with decimals. So you'll get 2.2361 repeating. And you can see that as we keep going, we are just going to get a long string of decimals for an approximation. And that's okay. That's what this method does. Sorry. So I'm just going to hammer out a few of these here and write them out for you, and then I'll discuss what we get. Now, I said at the beginning that Newton's method will converge. That's a fancy word that says it will kind of get closer and closer to the real answer the more you do it. I picked this example because we can compare to the true value. Now, in real life, when you're solving problems, you can't compare to the true value. Now, my first iteration was only accurate to before the decimal point. My second iterate here was 1 decimal place accurate. My next iterate was 3 decimal places accurate. And by the time I got to the fourth iterate, I had 1, 2, 3, 4, 5, 6, 7, 8 accurate. That's awesome. And by the time I get to the next one, they're all accurate. So Newton's method is an amazing method because it converges to the answer really quickly. It usually doubles every time you do an iteration. The number of decimal places that are accurate usually doubles every time you do an iteration. So Newton's method is really a high-powered approximation method, and I think of it as the final piece of the story. Now you're armed with knowledge in terms of existence of answers and how many they're supposed to be, and you've got the final tool, and you're empowered, and you can go and find it. And this is really a beautiful capstone topic to a lot of what you study in calculus. This method gets generalized in real life and is the way to solve a